Hello. I would like to briefly show you the repository of the Seymour project. It is a joint work with Tristan Figura-Wright, Rida Hadamani, Byung-Hak Wang, Evgenia Karunus, Vladimir Kolmogorov, Alex Mayburg, Peter Nelson, Mark Sandy, and Ivan Sergeyev. Everything starts in this basic file. Here we declare some notation that will be used throughout the project. For convenience, and we provide some very basic lemmas that are used everywhere. Next, we have these conversions where we kind of deal with the interface between type theory and set theory. For example, here this function converts something that is in union of sets to an element of sum type, which is essentially a disjoint union of sets. In this file, we provide some basic lemmas for working with the smallest types on one element, two element, three elements. In this file, we provide an auxiliary construction that decomposes a function of this type into this auxiliary function and then two bijections. Slightly different auxiliary construction is in this file. In the file sets.lean, we provide some basic lemmas about working with sets in lean. Signtype.cast, this file is based on the fact that total unimodularity is defined as the determinant being in the 0, 1, -1 set, which in lean is in mathlib it's encoded as signtype.cast.range. So this file provides helpful lemmas to talk about these expressions. And finally, a submodule spans. This file provides some auxiliary lemmas that will be used for working with standard representations of matroids. So this was the folder basic. Now for the folder metrics, we again start with some very basic lemmas about matrices. Then similarly to what we had previously, we have a conversion, but this time it's a conversion of matrices. Here you have a matrix indexed by sum type, like matrix indexed is like a standard block matrix is indexed by disjoint unions, and we convert it to a matrix indexed by unions of sets. Yeah, and we provide some API for it. This file provides some very basic lemmas about determinants. In this file, you find some things about linear independence in the context of matrices, like when are the rows of a matrix linearly independent. The file partial unimodularity is an auxiliary file where total unimodularity is built basically step by step for bigger and bigger square matrices. The pivoting file is very important. Here we start with some like basic properties of row and column operations, and then there are these important definitions. There is long tableau pivoting and there is short tableau pivoting. It's useful in many proofs. And there is a short file about signing of matrices. There is a short file about treating the column space of a matrix as a vector space, and it is about the basis of this vector space. And support metrics, it just talks about which positions of the matrix are zero, which positions of the matrix are non-zero. Again, some basic API about that. Finally, total unimodularity. This file provides a lot of lemmas because we talk about totally unimodular matrices a lot. The most difficult lemma was to prove that if you have a block matrix that has totally unimodular matrix A1 and totally unimodular matrix A2 along the main diagonal and the zeros elsewhere, that the resulting matrix is totally unimodular. And we also have some computable testing of total unimodularity with formal guarantees. So this was the matrix folder. Now finally we get to matroids. This is how we construct vectors from matrices, so-called matroids from matrices, so-called vector matroids. Yeah, we focus mostly on binary matroids. In this file, we talk about their standard representations. Again, there is a lot of API to be given. Then we define regular matroids as matroids that are represented by a totally unimodular rational matrix, and the rest of the file basically connects it to binary matroids with totally unimodular signings. Then some special cases, there is this R10 matroid, there is graphic matroids, co-graphic matroids, a little bit about duality of matroids and its relationship to their standard representations. And now the main three files of the projects are here, sum 1, sum 2, sum 3. In these files, we talk about 1 sums of matroids, 2 sums of matroids, and 3 sums of matroids. It starts with definition here, and this is some auxiliary lemmas that are not, some non-essential lemmas that are not proved, but the final result doesn't depend on them. So the first final result is that the one sum of regular matroids is a regular matroid. Similarly, in sum 2, we define on 3 levels, like what is the 2 sum of matrices, what is the 2 sum of standard representations, what is the 2 sum of binary matroids, and again we prove that if you have 2 regular matroids, their 2 sum is also a regular matroid. And the most difficult is sum 3.len. Here we define the 3 sum of matroids. Here the definitions are much longer, but again, in the end, we provide this very simple characterization that if ML is a regular matroid and MR is a regular matroid, their 3 sum is also a regular matroid. So there is like a corollary of this thing, which is called the easy direction of the Seymour theorem. And for the hard direction of the Seymour theorem, so-called decomposition direction, we only stated the theorem, but we haven't started proving it yet. And because this is like a lot of code and you as a reader might not know what's important, what's to read, there is this final file, seymour.len, and in this file we recall all non-trivial definitions that our final result depends on. And this recall command means that the thing that's written here is tested for definitional equivalence with the actual definitions in the project. So we cannot be, so even if we rephrase the original definition in slightly simpler words or something, we cannot be deceiving you. This file is formally verified for consistency with all the previous files. So here you can read really all the non-trivial trusted code, and you can read the final results. And here you get a guarantee that the entire proof of this thing, including all lemmas that it depends on, uses only these three axioms, which are standard axioms. If you use lean with classical logic, the same with two-sum, that it has been fully proved. There is no sorry in the proof. And finally, yeah, the definition of threesome is quite long, but after we do all of that, we can check that the proof that the threesome of regular matroids is regular, again, depends only on the three non-standard axioms. And that's all for now. Thank you for your attention.